Hi everyone. In this lesson, we'll explore two decision tree methods for entropy-based classification, ID3 and its advanced version, C4.5. Let's dive in. A decision tree is an algorithm used in machine learning and statistical modeling that simulates the decision-making process by modeling data in a tree structure. Each internal node represents a feature. Each branch represents a decision rule, and each leaf node represents a class or outcome. Decision trees can be used for both classification and regression problems. But in this lesson, we'll use its only classification ability. Several key concepts are essential to understanding decision trees. First, the root node is the top node of the tree. Next are the internal nodes within the tree, which divide the dataset based on specific features. Then we have the leaf nodes, which represent the final decision or classification result. Lastly, the branches are the lines that connect the nodes to each other. The entire dataset is represented in the root node, where it is determined which feature will be selected for the first division. This selection is made using methods such as entropy-based information gain, the Gini index, or the chi-square test. In this lesson, we will focus solely on information gain based on entropy. For example, in the decision tree on the screen, the entropy-based information gain criterion was applied, and it was determined that the first node should be weather. This means that the weather criterion contains more distinctive information compared to the humidity and wind criteria. We'll learn about two decision tree algorithms that use entropy, ID3 and C4.5. Before diving into these algorithms, it might be helpful to discuss some key concepts such as entropy, uncertainty, information, and information gain. In probability theory, entropy is defined as a measure of uncertainty about a random variable. In this lesson, we will use Shannon entropy, a fundamental concept in information theory. According to Shannon, entropy quantifies the average amount of information produced by a stochastic source of data. It measures the uncertainty or unpredictability of the random variable's possible states. Shannon's entropy is calculated based on the probability distribution of the random variables' possible outcomes. Therefore, the more uncertain the outcome, the higher the entropy. Shannon extended this approach to demonstrate that when there is less information, or in other words, more uncertainty, there is more potential for information gain when new data is obtained. Claude Elwood Shannon was a young engineer working at Bell Labs in the 1940s. One day, he began pondering over the uncertainty and information transmission in communication systems. These thoughts led him to his groundbreaking work that would lay the foundations of information theory. Shannon developed a method to understand the flow of information in both natural and man-made systems. In this method, he used a concept he called entropy to measure the uncertainty within a message. Entropy expressed how much information a message contained and how unpredictable that information was. Shannon published these ideas in his paper titled A Mathematical Theory of Communication. This paper formed the basis of modern digital communication and data compression algorithms. Thanks to his work, computers and communication systems became more efficient, opening the doors to today's information age. For a discrete random variable x with a probability mass function px, where x represents the possible outcomes, Shannon entropy hx is defined as hx equals summation px ix. Here, ix representing information is defined as ix equals minus log px. When we write ix in place, then it will be hx equals minus summation of px log px. Now, we can look at an example to compute Shannon entropy. Let x be random process of a coin toss. Since its two situations have the same probability, The entropy of X is found 1 as below. We know that process X has two states, heads and tails. Here, as soon as we know that the money is fair, we understand that both situations have the same probability. Then the probability in both cases is 50%. Then the entropy is calculated as 1. A decision tree divides multidimensional data into several subsets based on conditions applied to specific features. Choosing which feature to split on and determining the optimal splitting condition at each node involves solving a complex combinatorial problem. In a dataset with 20 samples and 5 numerical features, the C4.5 method might need to evaluate up to 19 different threshold values for each of the 5 features during the first branching decision. This results in 5 times 19 equals 95 possible branching criteria. Even with a small dataset, the number of possible decision trees can be extraordinarily large. Therefore, each branching decision must be made methodically and carefully to ensure the decision tree's effectiveness and efficiency. To address this complexity, methods such as information gain, the Gini index, and the chi-square test are employed. Ross Quinlan is an Australian computer scientist and a pioneer in decision tree algorithms. He is best known for developing the ID3 algorithm in the 1980s and its successor, the C4.5 algorithm. These algorithms have made significant advancements in the classification of data using decision trees and have revolutionized the fields of data mining and machine learning. Quinlan's work has made decision tree algorithms more effective and practical, contributing greatly to modern data analysis and artificial intelligence. According to Quinlan, decision tree branching should aim to maximize information gain. To achieve this, we need to identify the feature that reduces uncertainty the most. In the ID3 algorithm, each feature is evaluated individually to determine which one minimizes uncertainty the most. ID3 is designed to work with categorical data. During each iteration, the process begins by calculating the entropy of the entire dataset for all features. Next, the entropy for each feature, considering the classes, is computed and then subtracted from the initial entropy. The feature that provides the maximum information gain is selected for branching. Now, to understand ID3 method, we can look at an example. Here, we have a dataset with 4 samples, 2 features, and 2 classes. Our question is to find the first branching feature. First, we measure the overall uncertainty of the dataset. In this case, there are 2 classes, E and F, each equally represented, so the dataset's entropy reflects a balanced uncertainty about which class any given sample might belong to. So, the entropy of the dataset is found as 1. Next, we need to focus on the entropy of each feature separately. First, we look at V1 feature. For samples with value A, all belong to class E, meaning there's no uncertainty for this subset. For samples with value B, we have an equal mix of classes E and F. This subset has some uncertainty because the class is not consistent. When we combine these, the feature V1 reduces uncertainty significantly overall, so it provides a good split. Then, we can compute the entropy of V2. For samples with value C and samples with value D, each subset has an equal mix of classes E and F. Thus, there is the same level of uncertainty in each subset. Since neither subset helps in reducing uncertainty more effectively than the original dataset, this feature doesn't improve our knowledge about class distribution. The feature that provides the highest reduction in uncertainty, or the greatest increase in information, is considered the best for branching. Here, V1 reduces uncertainty more than V2 does. Even though the ID3 algorithm can solve many problems, Ross Quinlan improved it into C4.5 to address several limitations and enhance the performance of decision tree learning. For example, ID3 can work with only categorical data, but real-world data often includes continuous features. C4.5 introduced the ability to handle continuous attributes by finding the best split point in a continuous range. The second improvement was in pruning. ID3 does not include a method for pruning. Therefore, in ID3, overfitting cannot be avoided. On the other hand, C4.5 includes a pruning mechanism to simplify the tree by removing branches that have little importance, thus improving the model's performance on unseen data. The other detail is about missing values. ID3 does not handle missing values very well. C4.5 introduces techniques for dealing with missing data, allowing the algorithm to handle incomplete datasets more effectively by using probability-based methods to estimate missing values. Apart from these, C4.5 has additional features such as increased performance in large datasets, dealing with noise, and using gain ratio, but we will not talk about them here and will talk about its most primitive form. For categorical features, the calculation is done as in ID3, so we will only explain the algorithm for how the numerical feature is processed. First, all values in numerical feature are sorted. Then, an average value for each neighbor pair at sorted list is computed, and it is called as threshold. We'll have N1 threshold values. Each threshold is tested to branch dataset, and an information gain is computed. The threshold supporting the maximum information gain is chosen as the best. C4.5 algorithm uses pruning methods to reduce overfitting in the decision tree by making it more general. Pruning prevents the tree from fitting too closely to the noise and specific details of the training data. The C4.5 algorithm employs both pre-pruning and post-pruning techniques. Pre-pruning involves setting stopping criteria during the decision tree construction process to prevent further growth of the tree. The first approach is the using a minimum information gain threshold. If the information gain at a node is below a certain threshold, the node is not split further. This threshold is usually determined experimentally and prevents further branching when the information gain is insufficient. The second approach is the using a minimum number of instances. If the number of instances at a node falls below a certain value, the node is not split further. This criterion prevents overfitting to small data subsets and ensures a more general model. Post-pruning involves pruning the decision tree after it has been fully constructed. These techniques aim to make the final tree more general. The first approach is error-based pruning. This method replaces subtrees with leaf nodes by comparing the error rates. If the error of a leaf node is lower or equal to the error of a subtree, the subtree is pruned and replaced by the leaf node. The error rate is typically calculated using a validation dataset. The second approach is reduced error pruning. This method prunes subtrees if doing so reduces the overall error rate. It relies on the error rate on a validation dataset to decide on pruning. This method is effective in producing simpler and more interpretable trees. The third approach is rule post pruning. This method converts the decision tree into a set of if-then rules and then simplifies these rules. Unnecessary rules and nodes are removed, making the tree simpler. This approach helps in creating a more understandable and generalized model. You see a decision tree on the screen. The number of instances that fall on all leaf nodes is also written. If the tolerance value is given as 33% while performing error-based post-pruning on such a tree. How is post-pruning done? While the leaf labeled no under humidity receives 70% of the dataset in the parent node, The leaf labeled yes receives 30% of the instances. Since this value is less than the error tolerance value, the nodes labeled yes are ignored. Thus, the node labeled humidity and all nodes below it are pruned and replaced with a leaf node labeled no. If some samples are missing in dataset, there are two approaches to be followed. The first, instances with missing values are completely removed from the dataset. The second, missing values are imputed by some approaches. If the number of instances with missing values is large enough, then the first one may be chosen. For small datasets, the second approach should be applied. The title of deleting rows with missing data from the dataset is quite clear. However, there are many approaches to filling in missing data. We can summarize just some of them as follows. The first one is imputation with mean or median. The second one is probabilistic imputation. And the third one is imputation with KNN. Now we will see a calculation example. The question asks us to find the first branching factor for the data set given on the screen, using C4.5. At this point, I recommend you stop the video and do the calculations manually. Then you can continue and watch the solution. First, we should compute entropy for the dataset. It is found as 1. Then we make the X4 values unique and sort them. According to these sorted values, thresholds are computed. For each threshold, the values in the numerical attribute are categorized. In our example, values greater than the threshold are called A, and values less than the threshold are called B. Finally, the entropies of the new categorized versions of the X4 feature are calculated and the lowest uncertainty is selected. The entropies of non-numerical features are also calculated as we learned in the ID3 method. Among all features, the feature with the lowest entropy is selected. Here, the lowest uncertainty and therefore the greatest information gain is provided by X3. For this reason, X3 is selected as the first branching criterion at the root of the decision tree. Thanks for watching. We recommend that you attend class for in-class activities.